Welcome back. In this video, we will learn how to draw Lewis structures by applying the octet rule and the rules of valence. So Lewis structures, as we've seen, indicate the number of bonds between different molecules. And these are in the cases of covalently bound molecules, so groups of nonmetals. The first step to drawing a Lewis structure, given the molecular formula, is to count up the number of valence electrons. Let's take, for example, water. Water's molecular formula is H2O. There are 2 hydrogens and 1 oxygen. Each hydrogen has 1 electron. We know that because it's in group 1A. And the oxygen has 6 valence electrons because it's in group 6A. So there's a total of 8 valence electrons. If we have a substance that has a negative charge, what we do is we add an electron to those already contributed by the elements. So for hydroxide, it has 1 from hydrogen, 6 from oxygen, and then 1 from the negative charge. For each positive charge, we will subtract an electron from those contributed by the elements. For hydronium ion, we have 3 oxygens, so 3 electrons, 6 from the oxygen, but we subtract 1 because of that positive charge. So it has a total of 8 valence electrons. The next step is to write out the atomic symbols of each element in the molecule and connect those atoms with a single bond between the central atom and the exterior atoms. In order to identify the central atom, you need to be able to determine their relative electronegativities. The element with the element that is least electronegative will go in the center of the molecule. The only exception to this is when hydrogen would be the least electronegative element. Because hydrogen can only ever form 1 bond, it can't be in the center forming multiple bonds. Then what we do is we distribute the electrons as lone pairs to the atoms, starting with those on the exterior, in order to complete octets for each atom. Finally, we evaluate. If there's not enough electrons to make every element satisfied with an octet, then we make multiple bonds between the atoms that are missing the electrons in order to complete the octet. So let's do an example here by drawing the Lewis structure for nitrosyl chloride, NOCl. The first step is to count up the number of valence electrons. Nitrogen is in group 5, so it has 5 valence electrons. Oxygen is in group 6. Chlorine is in group 7. When we add these up, we get a total of 18 valence electrons. The next step is to write out the atomic symbols and put the least electronegative element in the center. When you compare these elements, you see that nitrogen must be the least electronegative of them because it is farthest to the left. Now, perhaps you were a little bit puzzled trying to identify this, because when you look at nitrogen, oxygen, and chlorine, we know that the electronegativity increases as we go up and to the right. So you might wonder, what's the electronegativity difference between elements that are in contradictory positions? For example, oxygen is farther up than chlorine, but chlorine is farther to the right. So using this trend of increasing electronegativity as we go up, oxygen should be more electronegative. However, if we use the trend going from left to right, chlorine should be more electronegative. You should know that oxygen is more electronegative than chlorine. There is a mnemonic, if you would like to memorize it, that goes through and looks at the electronegativities for some of the nonmetals. And it is for our clam bake, never bring internationally shipped canned hams, please. That stands for fluorine, oxygen, chlorine, nitrogen, bromine, iodine, sulfur, carbon, hydrogen, and phosphorus. So the order from high to low of the nonmetals is fluorine, oxygen, chlorine, nitrogen, bromine, iodine, sulfur, carbon, hydrogen, and phosphorus. The most important things here are to recognize that oxygen is more electronegative than chlorine, and that despite the physical difference between carbon and hydrogen on the periodic table, they're actually quite close, and therefore the carbon-hydrogen bond is not polar. All right, let's go back to this problem. So what's the least electronegative element? It's got to be nitrogen. Okay, so it goes in the center, and we draw then single bonds between the nitrogen and each other element. Okay, so at this point, we've used 4 electrons. We have 14 left over. Now we distribute the electrons to the exterior atoms as lone pairs to try and complete their octets. We put 6 on the chlorine, put 4 on the nitrogen, and 4 remaining on the oxygen. Now we'll see here that this is an unhappy situation. We have chlorine and nitrogen with satisfied octet, but oxygen does not. If you had put the lone pair, an extra set of lone pair electrons on the oxygen instead, it would have been happy and nitrogen would have not been happy. Either way, those elements are not happy. And so what we do is we draw multiple bonds between the elements in order to satisfy them. So we take two of the electrons from the nitrogen in the center, and we donate them to be in between the oxygen and the nitrogen. Then when we reevaluate the Lewis structure, we see that all elements indeed have 8 electrons. Chlorine has 6 in the form of lone pair electrons, and then 2 shared here. Nitrogen is sharing a total of 6 electrons between the 3 bonds, and then has 1 set of lone pair electrons. And the oxygen has 4 electrons here in the bonds, and 2 sets of lone pair electrons around it as well. All right, here's a problem for you to try. Pause the video and see if you can figure this one out on your own. Welcome back. So in this question, it's asking you to identify how many bonding and non-bonding electron pairs there are in CF4, carbon tetrafluoride. First step is to count up the number of electrons based on the valence electrons. Carbon has 4, and there's a total of 28 from the fluorine atoms, 7 from each fluorine. That's a total of 32 electrons. We then put excuse me, the carbon in the center, being the least electronegative element, and draw single bonds between carbon and each of the fluorines. And then we can distribute those electrons that are remaining. We've used up 8 so far, so we have 24 left. We put 6 on each of the fluorines, and that uses all 24 electrons. So in this molecule, then, we have 4 bonding pairs and 12 non-bonding pairs. Let's try one more. This one's wants you to identify what's the structure within this N2H2 molecule. pause the video and see if you can figure this one out on your own as well. All right, what's the first step? It's to identify the number of valence electrons. For hydrogen, there are 2 total valence electrons, 1 from each hydrogen. Each nitrogen contributes 5, and so we have a total of 12 valence electrons. Now, when it comes to drawing the bonds and the basic structure, we've given you a hint, and that's that each nitrogen is connected to 1 hydrogen. So it would look something like this. We have nitrogens. Essentially, we have 2 centers, if you will, 1 with each bond to hydrogens. And then we start out with a single bond between the nitrogens. Then we try and distribute the remaining 6 electrons. When we do that, we can see that one of the nitrogens is satisfied, but the other is not. So in order to satisfy both, we need to take one set of the lone pair of electrons and share it. So that way we have 2 bonds between the nitrogens. When we do this, we see that each nitrogen now has 3 bonds, which is typically what we expect for nitrogens, and 1 set of lone pair electrons. Again, what we expect. So then what we see here is we don't have a triple bond between the nitrogens, nor a single bond. However, excuse me, each nitrogen does have 1 lone pair. So that's it for this video as well. Thank you for watching. Have a great day.